we continue with our discussions on optical parametric oscillators. Can I just pass it on in the back? So remember, what we have seen is if you take a nonlinear medium possessing a finite chi2, if you launch a frequency omega p pump and a signal omega s with omega p is equal to omega s plus omega I, then it is possible to amplify the signal at frequency omega s by the process of parametric down conversion. So that means this particular device acts like an amplifier. And also we have seen that we need to satisfy the condition Kp is equal to Ks plus Ki, or Kp is equal to Ks plus Ki plus K. This is QPM. This is birefringence phase matching. It's possible to tune the frequency at which this amplifier will work by adjusting these conditions. So for a given pump and signal frequency, we have to satisfy the energy conservation equation and the momentum conservation equation, either the first one or the second one if there is periodic domain reversal. So this is a very interesting device because it amplifies signals at frequency omega s, and the value of omega s can be changed by changing the orientation of the crystal, for example, so that birefringence phase matching is satisfied by different sets of wavelengths, signaler and idler, or by choosing different k values, the periodic domain reversals, so that you can have a tunability. So once you have an amplifier, you can actually put the amplifier within a pair of mirrors and convert the amplifier to an oscillator. An oscillator is a device which is a source of radiation. So if I put this amplifier between a pair of mirrors, and if I launch light at omega p into this crystal, let me assume the mirrors have no reflection at the pump frequency. So the mirrors are completely transmitted at the pump frequency. So when pump enters the crystal, the first thing that happens is it can spontaneously down convert to a pair of frequencies omega s and omega I that satisfy the pair of energy conservation and momentum conservation conditions. Once that happens, then I can have these two mirrors so that they are highly reflecting, for example, at the frequency omega s. So the omega s light, when it propagates through this, it gets amplified. Once after having generated spontaneously the signal photons get amplified when they reach the second mirror here. At this point, if the reflectivity at the signal frequency is high, part of that signal is transmitted and majority of it is reflected back into the cavity. And as it propagates here, in the reverse direction, I don't satisfy the phase matching condition. So the signal just propagates and gets reflected from the first mirror, and then again it propagates in the forward direction, getting amplified. So what's going to happen is, if the reflectivities of the mirrors are very high, most of the energy of the signal is reflected back and forth inside the cavity, and it grows in magnitude. I can have a situation where the mirrors are transmitting at the idler frequency, so omega I actually does not reflect back and forth, it escapes from the cavity, but the omega s signal is completely, is sort of reflected within the cavity and has a very high energy density inside the cavity. So this is called a singly resonant oscillator, where you are resonating only one frequency, omega s. So what will happen is, if I put in a pump omega p, the gain inside the crystal depends on the intensity of the light at omega p. Remember, the gain coefficient depends on the nonlinear coefficient of the crystal, and it also depends on the intensity of the pump wave. So if my intensity of the pump wave is sufficiently high, what can happen is the gain suffered by the signal in one round trip can be compensated by, or can compensate the loss suffered by the signal in one round trip. So the condition for oscillation is, as the signal does one round trip inside the crystal, that means it starts from the mirror, goes to the second mirror, reflects, comes back, reflects. So that's one complete round trip. If in one round trip, the loss is compensated by the gain, then I will have a strong signal coming out from here. And of course, omega I will also be coming out. And unused omega p will also be coming out. So I can actually make a source of radiation at omega s by taking this nonlinear crystal, putting it inside a cavity. The cavity will resonate one frequency omega s, and so what will happen is, just like a laser, it actually is a coherent source. In a standard laser, like helium neon laser or ruby laser or Nd:YAG laser, the amplification is brought out by population inversion. And that depends on the energy levels, available energy levels of the atoms. This amplification is a nonlinear process, and by orienting the crystal in different directions, I can actually change the frequency at which it will amplify. So this is a tunable source of radiation, and it can have a very broad tuning range independent of the energy levels. There is no absorption by the crystal. It's simply a nonlinear conversion process. So just like a laser, I need to satisfy some conditions of round trip gain, and also the frequencies which will oscillate here are determined by the standing wave patterns inside the cavity. Not all frequencies are allowed, because only those frequencies in which the phase change in one round trip is exactly equal to multiple of 2 pi can sort of build up inside the cavity. I can also have a situation where not only the signal is reflected, but also the idler is reflected back into the cavity. In which case, I will have to have standing wave conditions for omega s and standing wave conditions for omega I. And again, the round trip gain must be equal to loss. Yes, Mohit.
So omega s and omega I are determined by the orientation of the crystal.
Yes.
Now, after this, the further condition should also be that it should be, the standing wave condition should also be imposed.
Yes.
Now, in case when omega s and omega I satisfy the orientation of the crystal and do not satisfy the standing wave conditions.
So I'll come to these numbers. What is, first of all, one thing is that it's not that amplification can take place only at one frequency. We have seen that there is one frequency for which this condition is exactly satisfied. Okay, that is the maximum gain. If my signal frequency deviates from this condition, delta k becomes finite, gain drops.
It becomes a thing.
Yeah, it's a drop. There is a drop in gain, but there is still gain. As you change so there is a range of signal frequencies over which I will get gain from the crystal for a given orientation of the crystal. Once I fix the crystal direction, there is one pair omega s omega I which exactly satisfies this condition for delta k is equal to 0. So I get maximum gain. If omega s is slightly different from this number, delta k is not equal to 0, but there is still gain. Until, remember we had obtained a condition, until g square is greater than delta k square by 4, I have gain. And after that, the hyperbolic functions change into sine and cosine functions rather than the hyperbolic functions, and the gain drops. So I will give you some numbers later on that the range of frequencies over which I can achieve gain is called the gain bandwidth, and that will contain many modes, many standing wave patterns of this cavity.
So, but in order to use it as, for a laser,
yeah,
we need to ensure that the omega s that we want,
yeah,
the cavity length should be in accordance with that omega s.
Yeah, but these omega s differences are very, very small. We'll get some numbers. Even in a standard laser like a helium neon laser, you are not getting one wave frequency. Usually you are getting 3 or 4 frequencies coming out, which are very closely lined with each other.
But then peak, the intensity peak is at a single frequency.
Yes, but the intensity difference will not be significantly different. I mean, the intensities are not significantly different. So I can have, typically in a laser, I will not have a single frequency oscillation. There are multiple frequencies coming out. I need to do something special to make the laser single frequency laser. I need to put a device inside the cavity, like a Fabry-Perot Etalon, to make sure that there is only one frequency that comes out of the laser, which means it will have a large coherence length. Delta lambda becomes very small, unless it will not become that small unless I do something special on inside the laser cavity. And apart from that, there is also a problem. That frequency can keep fluctuating. The laser can be oscillating at a single frequency, but that frequency can be moving back and forth here and there slightly, because as the temperature changes, the length of the cavity will change. And that change in length of the cavity means the frequencies of oscillation will change. So there is a small fluctuation. So if I need to have a frequency stabilized laser, I need to give a feedback and make sure that the frequency at which the laser is oscillating remains fixed. Okay, so even standard lasers do not give me single frequency unless I do something special. So this will give me for one frequency, which will have the largest gain. But usually there is it's a single frequency output that comes out from here. The advantage is it's tunable and over a large range of wavelengths, independent of the energy levels of the crystal here. There's no absorption. Unlike a standard laser where there is population inversion created by absorption and emission. Okay, so I can have a situation where both are oscillating, and that's called a doubly resonant oscillator. So you have a singly resonant oscillator and a doubly resonant oscillator. So in a doubly resonant oscillator, both the signal and the idler are resonating inside the crystal. Both are forming standing wave patterns inside the cavity. The mirrors have high reflectivities both at omega s and at omega I. And I will show you that this imposes severe conditions on the stability of the cavity. Because if the cavity has a slight changes, then the laser becomes unstable. The frequencies are shifting back and forth very, very violently if you don't maintain the cavity in a precise condition. I will also show you that the power required for a DRO is much less than power required for an SRO. What is the pump power? See, the question is, how much pump power do I need to make the laser oscillate? So I take a crystal, say lithium niobate, put it inside a pair of mirrors, say 98% reflecting mirrors, certain length of the cavity, 5 centimeters. So what is the power required at omega p for this to start lasing, to start emitting light? I must make sure that the round trip loss becomes equal to round trip gain. The round trip loss is fixed by the reflectivities of the mirrors and any other loss that takes place inside the cavity, like absorption, scattering. The gain is determined by the intensity of the pump. So for a given loss inside the cavity, I will have a threshold pump power. I will have a threshold pump intensity or a threshold pump power at which this will start to oscillate. It's like any other laser. In any other laser also, I need a certain minimum current in the helium neon laser cavity or a minimum pumping power before the laser starts to oscillate. Or in a semiconductor laser, I need a minimum current to make the laser start to emit light, because I need to overcome losses in the cavity. Also note that the oscillator starts by parametric down conversion, spontaneous parametric down conversion, parametric fluorescence. That is the noise that starts the laser to oscillate. A noise is required for any oscillator to start. So first what we will do is look at a singly resonant oscillator, discuss a singly resonant oscillator, and then look at a DRO. So singly resonant oscillator. So let me draw the system. So here is my crystal of length L let me assume that the crystal fills the entire cavity. So I have light at omega p frequency coming from here. So the reflectivity of the mirror at pump is 0. Reflectivity of the mirror at pump is 0. Rp is the energy reflectivity of the mirror at the pump frequency p, omega p. Rs, the reflectivity of the signal frequency, let me assume it is R1, and this is R2. They could be different, they could be equal. For example, I could have this to be 1 and this to be some finite value, 98%. I could have both finite numbers, whatever it is. And then finally, Ri is equal to 0 for both the mirrors. So the mirrors are highly reflecting at the signal frequency and completely transmitting at the pump and the idler frequency. So the pump enters, then just goes through the crystal. So the way I will analyze the problem is two things. One is I need to find out what are the frequencies of oscillation of the cavity. And secondly, what is the threshold power required for the laser to start oscillating? So first thing is, what are the frequencies of oscillation of this cavity? Remember, the phase shift in one complete round trip must be an integral multiple of 2 pi. Okay? So what is the condition I will get? 2 times Ks times L is equal to I am assuming in writing this condition that the mirrors are not introducing any phase changes, and the phase change is primarily because of propagation through the crystal. If there were phase changes suffered because of the mirrors, I have to add those phase changes to KSL. So Ks times L is the phase change in going from here to here. Another Ks times L is the phase change in going from here to here. So the total phase change in one round trip is 2 times KSL, and that must be an integral multiple of 2 pi. So this gives me, this goes off, 2 goes off. So omega s by c into L is equal to m pi, or omega s is equal to m into pi c by this is omega by c, omega ns. Sorry, there must be a frequency, a refractive index here. Ns is the refractive index of the medium at the frequency omega s. The propagation constant inside the medium is omega by c times the refractive index. So the frequency divided by c times ns into L is equal to m pi. So the frequencies of oscillation are m into pi c by lns. So these are discrete frequencies, and what is the difference? Can we calculate what is the frequency spacing between the modes? So these are the modes of oscillation of this cavity. These are the modes of oscillation of this cavity. That means the modes that can survive within the cavity, which form a standing wave pattern inside the cavity. So what is the so in terms of nu, let me write this as nu s is equal to omega s by 2 pi, which is equal to m into c by 2 times L times ns. This is the angular frequency omega s, and that's the frequency of oscillation. Now, assuming that the frequencies are not very far spaced, which means, and I'm assuming that ns does not change much as I change my frequency, so the intermode frequency will be how much? Intermode spacing, c by 2 times L times ns. So let me put some numbers here. So let me take a cavity of 5 centimeters length. What is the value of ns? Approximately 2. For lithium niobate it's 2, otherwise 1.8 for some crystals. So it's of the order of 2. So delta nu s comes out to be 3 × 10⁸ by 2 into 5 × 10⁻² into 2, which is equal to How much is it? 1.5 into 10 power 9 hertz. So that's 1.5 gigahertz. The frequency spacing is about 1.5 gigahertz. Every 1.5 gigahertz, there is a possible frequency of oscillation within the cavity. There is no condition on omega I, except that this frequency omega s plus omega I must be equal to omega p. Okay, so omega s is fixed by the cavity. These are the only allowed frequencies. Omega p is what I have chosen. So omega I automatically gets fixed. Knowing omega p and these omega I can calculate what are the omega i's which will be coming out of the crystal. Okay. Now I need to calculate the threshold condition. What is the power required, or what is the intensity of the pump required for the oscillator to start? So what do? This is my crystal again. That's a mirror. Here, there is another mirror here. Okay, so let me start with an amplitude ES0. So at this mirror, the amplitude incident is ES1. The amplitude reflected is ES2. The amplitude incident here is ES3. And the amplitude reflected is ES4. That's one round trip. Starts from here, goes, gets reflected, comes back, gets reflected, and comes out. So what is the condition for oscillation? ES4 must be equal to ES0. If that happens, then every time you have a round trip, whatever you have lost, you have gained, and this continues forever.
So this is in the steady state?
Steady state, yes. We are looking at steady state situation where you have continuous pump coming in from here, and the signal will adjust itself to a value such that there is a complete compensation of loss by the gain. So now to simplify the analysis, let me assume the only loss mechanisms are the two mirrors, which have a finite reflectivity of R1 and R2. Yeah?
Sir, in this case, when the omega s is getting reflected,
Yeah, yeah.
sir, there is only omega s. So can't there be a spontaneous conversion from omega s to omega p? Suppose
If omega s and omega I are strong enough, both of them, it's also possible. Back conversion to omega p, it's possible. Surely it's possible. But in the first analysis, to get the threshold value, I don't have to worry about it, because at threshold, the intensities at signal and idler are not very high. Beyond threshold, once it starts to oscillate, there is a lot of power at omega s inside the cavity. There is omega p, and there is also omega I, because it's getting generated inside the cavity, but getting out of the cavity, I need to look at back conversion also. Which means when I actually have to solve those equations to get the signal power that is coming out finally. We're not going to do that here. What I'm going to do is, what is the pump power required to start the laser, to start the oscillator? When the oscillator starts, the signal powers are not very high. It's just like calculating threshold. At the threshold, the signal powers are not that high, and we can estimate very well what is the pump electric field required or pump intensity required to satisfy the condition that loss is equal to gain. Okay?
so sir, in that case, we need to, this process will also be a process of loss.
Yes, for the signal. Yes, exactly. The back conversion to omega p is another loss mechanism for this pump, for the signal. Yes. Okay, so remember we had obtained an expression for gain. Can you recall? Es of z. What is the expression for the gain with delta k is equal to 0? And only the signal incident. Let me write out the equations. Des by dz is equal to I kappa s EPEI star. DEI by dz is equal to I kappa I EPES star I differentiate the first equation. D square Es by dz square is equal to I kappa s EP dEI star by dz, which is minus I kappa I EP star Es, which is equal to kappa s kappa I mod EP square Es. Now can you tell me what is the expression? So we call this G square Es. What is the solution of this equation? And cos hyperbolic, right? So what is the condition I should put? So for example, the solution of this equation is Es of z is equal to A sin hyperbolic Gz plus B cos hyperbolic Gz. These are the two differential equations. I am assuming pump 2 remain constant, no pump depletion. Then I differentiate, I get this equation.
At 0, z equal to 0, signal is 0.
No, signal is finite.
Okay. Es 0, yes.
So at z is equal to 0, Es is equal to Es0. This implies B is equal to
Es 0.
Es0. How do I find A?
From
EI is equal to 0.
differentiate Es.
No, I don't have to. Here, EI is equal to 0. Yeah. At z is equal to 0. So, DES by dz is equal to 0 at z is equal to 0. That means, what is the value of A? A is 0. So, I will simply get, so at z is equal to 0, EI is equal to 0 implies DES by dz is equal to 0. This implies A is equal to 0. So, the solution is ES of z for large Gz it becomes exponential, but otherwise it's cos hyperbolic. Okay, so this gives me the expression for the signal field in going from, let me call this mirror M1 to mirror M2. So from M1 to M2, the signal field increases, gets multiplied by factor cos hyperbolic Gz, while going from M2 to M1, there is no multiplication factor. Because in the reverse direction, delta K is not equal to 0. In fact, delta K is very large. Because delta K, what will be the delta K for reverse direction? You will get Kp plus Ks plus Ki or minus Ki. You can do. But it will not be able to satisfy this condition. So the pump going in this direction, signal going in this direction, there is no amplification. So there is, because there is no pump in the reverse direction, so there is no amplification and Es remains the same. Okay, now, so let me calculate. So I need to calculate from ES0 what is ES1, ES2, ES3 and finally ES4. Now can you tell me what is ES1? So ES1 is equal to ES0 cos hyperbolic G times L. The length of the crystal is L. Let me draw the figure here again. So these mirrors have reflectivities R1 and R2. So what is ES2? Square root of R2 times this. Remember, R2 is the energy reflectivity and these are electric fields. So the energy reflectivity is R. So the amplitude reflectivity is square root of R, assuming no phase change in reflection. Otherwise, I will have an exponential I, some phase factor. So it will be square root of R2 ES0 cos hyperbolic GL. ES3 is in this back in the first mirror, which is the same as ES2. And then ES4. Another multiplication by square root of R1. the field starts from here, gets amplified in reaching here, gets reflected by a factor root of R2, then it doesn't get amplified, it just propagates as such, then it gets reflected by the mirror M1 with the reflectivity square root of R1, amplitude reflectivity square root of R1, and that's the field after one round trip. And this must be equal to E0. So I get a condition that cos hyperbolic, let me call this cos hyperbolic, I put a subscript threshold GTH is equal to 1 by square root of R1 R2. And G, remember G square was equal to kappa S kappa I mod EP square. And this is omega S d by C n S, omega I d by C n I mod EP square, which is equal to omega S omega I d square by C square ns ni mod EP square. So the gain coefficient G depends on the nonlinear coefficient D and the electric field at the pump frequency. And the electric field at the pump frequency depends on the intensity of the pump inside the crystal. And that will depend on the power of the pump that I'm feeding in and what I'm doing to focus. If I'm focusing with the same power, the intensity will increase. So EP will increase if I focus the beam inside the cavity. So depending on the reflectivities of the mirrors and the length of the cavity, there is a value, threshold value of mod EP square. And that means a threshold intensity of the pump. That will be required for the oscillator to start. So if you don't put enough pump power into the crystal, if you don't have enough pump power coming from here, it will not oscillate because the gain is less than the loss. So as you increase the pump power incident into the crystal, there will be a critical point at which this becomes equal to the left hand side becomes equal to right hand side, and then it starts to oscillate. And if you increase the power beyond this, pump power beyond this, the signal will increase, just like a laser. Now, R1 and R2 are very close to 1, 98%, 99%, because I need to have a good resonator, which means I need to reflect most of the light inside the cavity so that the intensity of the signal inside is high. So the right hand side is very close to 1. So cos hyperbolic x is close to 1. So what do I do? I can expand. To get an approximate expression for G threshold, I can expand cos hyperbolic G threshold L, knowing that that value is close to 1. So what is the expansion of cos hyperbolic x for x close to 1? Can you find out? Yeah. Cos hyperbolic G threshold L when it is close to 1. Because I know R1 and R2 are close to 1. Yes. So cos hyperbolic G threshold L is approximately equal to 1 plus at x is equal to 0, cos hyperbolic is 1. So it has to be 1 plus something. Okay. So I can substitute this into this equation for the threshold and get an approximate equation for G threshold because R1 and R2 are close to 1. And if I assume, for example, so let me, so this gives me 1 plus G threshold square L square by 2 is equal to 1 by square root of R1 R2, or G threshold is equal to, so this is 1 by square root of R1 R2 minus 1 into square root of 2 by L. Raised per half. Okay. So how do I relate this to the power of the pump? So G square depends on EP square like this. So what do? How do I calculate IP or PP? I must replace mod EP square by the intensity of the pump. How are they related? Yes, so I have IP is equal to NP by 2C mu 0 mod EP square into, that's all. So this implies mod EP square 2C mu 0 by NP into IP. So G threshold becomes omega S omega I d square by C square ns ni into 2C mu 0 by NP IP threshold is equal to square root of 2 by L 1 by square root of R1 R2. So that gives me an IP threshold. So 1 C goes off and I get C NP NS NI by,
So this is the left side is the square of G. The equation that you have written.
okay, that's G square.
So right side.
Yeah, so I must remove this. Sorry, yeah, this is 2 by L square and this goes off. Yeah, thank you. So IP threshold is C NP NS NI by 2 mu 0 omega S omega I d square. So that factor of 2 goes up from here, L square 1 by square root of R1 R2 minus 1. Okay, so let me estimate some numbers. Let's put some numbers and calculate, okay, what is the threshold intensity required. So that we have an idea, is it in gigawatts per square meter or is it megawatts per square meter or is it watts per square meter? We have to be clear whether it is at all feasible. So let me substitute the numbers. Now we do a quick calculation. Now, so IP threshold, so this is C, which is 3 10 to the power 8 meters per second. What do I substitute approximately for NP, NS, NI? Approximately 2 into 2 into 2, so that's 2.1, 2. Etc. So let me substitute this as 8 divided by 4 pi 10 to the minus 7 is mu 0. Now omega S is 2 pi C by lambda S. There is no refractive index coming in omega S. It's a frequency. So I will have 4 pi square C square by lambda S lambda I. I'll substitute lambda S lambda I. So let me assume lambda P is equal to 0.6 micron. This is the same number we had used last time. Lambda S is 1 micrometer and lambda I comes out to be 1.5 micrometers. And let me take a length of 5 centimeter. And what is the approximate value of D? 30 10 to the minus 12 for lithium niobate. So 3 10 to the power 11 minus 11 meters per volt. And let me assume R1 is equal to R2 is equal to 0.98. So 4 pi square C square by lambda square, which is 1.5 10 to the minus 12 into D square, which is 9 into 10 to the minus 22 into L square 25 10 to the minus 4 into 1 by r minus 1, 1 by 0.98 minus 1, which is 0.02 by 0.98. Can somebody multiply all the numbers and just I leave the factors out? So I have something into, okay, so it's 10 raised power 8 from here, minus 12, plus 7, minus 16, plus 22, plus 4. So I have 10 power, how much is it? 3. Yeah, plus minus 13, right? Plus 13, yeah. And then what is the factor? So the remaining factors, if I multiply,
So 3.6 into 10 to the power 8.
Forget about all the factors. I'm forgetting about the 10 to the power.
Yeah, so I'm telling you the answer.
Actually, you are getting the total answer. What is the answer?
3.6 into 10 to the power 8. Sort of.
ज़्यादा आ रहा है. एक मिनट. You should get something like 6 10 to the minus 7. You will get something like 6 megawatts per square meter. Anyway, you just calculate, multiply, and it comes out to be of the order of 6 megawatts per square meter. So what is the power required? How do I estimate? I must have some area. What area do I take? 1 centimeter square? That's large. Usually laser beams are much smaller in size, few millimeter. Okay? So let me take 1 millimeter square area. Let me assume an area of 1 millimeter square. So the pump power threshold is IP threshold into S, which is 6 10 to the power 6 into 10 to the minus 6 watts. Maybe 6 to 10 watts of power is required for the oscillator to start. So that's a lot of power. 7.3? Okay. That's what I said, between 6 and 8, 6 and 10. It's of the order of about 10 watt of power is required for the oscillator to start. And if your pump power is less than 6 watts, in this example, the oscillator will not start because there is not enough gain provided by the crystal for overcoming the loss in the cavity, which is because of here finite reflectivity of the mirrors. In fact, the loss will be slightly higher because there is also scattering loss, there are diffraction losses, there are other kinds of losses in the cavity which we have not taken into account here, just to get an estimate of the numbers involved, because I will show you that in a doubly resonant oscillator, the power requirements are much lower, about a factor of 100 down compared to this. Okay. Now, we have a quiz? Next time, when? Wednesday? Okay. Now, I need to estimate two things. I've already estimated one thing, the frequency spacing between modes, 1.5 gigahertz. I need to know what is the frequency region over which this oscillator will provide gain. Is it of the order of 1.5 gigahertz or much larger or much smaller? and you'd have this number. Now, I had left a problem to you for calculating the bandwidth of a second harmonic generation. I need to do a very similar thing here. I need to calculate, so for example, I have delta k is equal to 0 at some signal frequency omega s is equal to omega s 0, and the corresponding idler frequency omega is equal to omega I 0. The question essentially is, this amplifier provides amplification over what range of signal frequencies? So if I take this crystal, I don't put it inside the cavity, but I look at it as an amplifier. So if I take this crystal and I launch pump and signal, then at one particular frequency pair, there is maximum gain, where I satisfy delta k is equal to 0. Now, if I change my omega s, keeping omega p constant, I will not have delta k is equal to 0, and the gain will drop. I can't use the solution that we have obtained earlier, because now delta k is not equal to 0. In fact, we had done this in the class. With delta k finite, we had obtained an effective gain, which was square root of g square minus delta k square by 4. So as delta k increases, the effective gain starts to fall, the gain starts to fall, and so there is a certain range of frequencies over which the amplifier will provide gain. Now let me give you an expression for this, and I will leave it as an exercise for you to please do it. If you have difficulties, we will discuss in this class, but please raise this issue. If you have a problem in deriving this expression, we will come back and calculate here, okay? So, and this is under some approximation. I leave for you to find out what the approximations are. You need to make a Taylor series expansion and so on, but the frequency range is approximately C by L times I'll tell you what these coefficients are. N at omega is 0 is N at omega is 0 plus omega is 0 dN by d omega at omega is 0. What is this quantity? Have you seen this before?
Expansion of.
Yeah, but what is this quantity? N capital N. Group index. The velocity at which the group velocity of the wave in the medium is determined by this number, this value of index, and not the refractive index, n. Small n defines the phase velocity, capital N defines the group velocity. If you go back and look at wave propagation in the medium, the phase velocity, the rate at which the phase is propagating is determined by small n, c by small n. The velocity at which the wave packet is propagating is determined by c by capital N. So this is the group index at signal frequency, and that's the group index at the idler frequency. Similarly, I have n of omega I 0 is equal to n of omega I 0 plus omega I 0 dN by d omega at omega I 0. Okay? So given a refractive index of the medium, I can actually calculate the group index at the signal frequency and at the idler frequency. So approximately, the range of signals over which the amplifier can provide gain is determined by this condition. The first thing you notice is that if you go to a position of degeneracy, what is the meaning of degeneracy? Omega I 0 is equal to omega I 0. The bandwidth becomes infinite according to this formula. But I can't use this formula, I must go to the next higher order term in my Taylor series expansion. Okay, so it doesn't mean infinite bandwidth, it means that the bandwidth becomes very large. So if you want a large bandwidth, you need to operate near degeneracy of the parametric amplifier. Then you will have a large bandwidth. Otherwise, your bandwidth is reduced because of the difference in these numbers. Okay, so let me just give you some typical numbers. This group index difference for the case which we have considered as lambda p is equal to 0.6 microns, lambda s is equal to 1.0 microns, and lambda I is equal to 1.5 microns. The group index difference delta omega s0 minus n of omega I0 is approximately 0.05. And so delta nu comes out to be 3 10 to the power 8 by 5 10 to the minus 2 into 0.05. How much is that? So 3 by 25 10 to the power 12. How much is that? 12 into 120 gigahertz, much larger than 1.5 gigahertz we had calculated. So it looks like this. You have the gain is provided like this, and you have the modes. So this spacing is about 1.5 gigahertz, and this width is about so there are a large number of closely aligned frequencies within the entire gain bandwidth. It's not, I'm not restricted by the fact that the gain bandwidth is smaller than the mode spacing. The mode spacing is much smaller than the entire gain bandwidth. The other thing I need to estimate is this. The way I've drawn it is as if they are well resolved frequencies. What determines the width of this, each line? Have you studied Fabry-Perot interferometer? What determines the width of these lines? Reflectivity of the mirrors, the finesse, the coefficient of finesse of the resonator. And let's give you an expression. If you have forgotten, please go back and read Fabry-Perot. So the width of each mode is approximately C into 1 minus R by 2 pi ns into L. And if you take R of 0.98, delta nu comes out to be 8.8 megahertz. So that's why I've drawn the width of these lines to be much smaller than the spacing between these lines. So this width is about 9 megahertz. Width of 9 megahertz approximately, intermode spacing of 1.5 gigahertz, and the overall gain bandwidth of 200 gigahertz, on 120 gigahertz. So, okay, I think we'll stop here. I'll continue with this little bit of discussion on this modes here, and then we move on to doubly resonant oscillator. And again, we need to calculate what is the threshold power required for the doubly resonant oscillator.